Welcome to the Explainer. Have you ever written a Python script that just kept growing until it eventually turned into this massive, unreadable monster? Well, today is your rescue mission. We're going to be engineering modular Python using the ultimate blueprint, functions.
Here is our agenda for today's factory tour. First, we'll fix the tangled mess, then break down the anatomy of a function. After that, we'll manage the data flow, understand variable scope, expand your Python toolkit, and finally, bring it all together into a complete modular ecosystem. Let's jump in. Section 1. Fixing the tangled mess, moving to modular coding.
We've all been there, right? Writing linear, monolithic code that turns into a literal tangled mess the moment it scales up. The fix for this is the structured assembly line of modular programming. By dividing a massive program into independent blocks where each has its own specific job, you transform total chaos into absolute clarity.
And this modular approach hands you 4 massive upgrades. First, readability. It turns complex logic into plain English. Second, reduced length. This kills the absolute nightmare of rewriting the same code over and over again. Third is reusability. You write it once and you deploy it everywhere. And fourth, parallel development. This is a real game changer because it means you and your team can actually code at the exact same time without breaking the whole system. Section 2. Anatomy of a function. Building the basic machine.
Now, building one of these function machines requires strict syntax. You always kick things off with the def keyword, followed by your unique identifier. Then, inside the parentheses, you've got optional parameters to catch incoming data. You cap that off with the mandatory header colon. Then, and this is Python's golden rule, your structural indentation physically defines the function block. If you step outside that indent, well, you're off the machine.
So how does this actually run? Python doesn't just read top to bottom like a simple script. It intentionally jumps. Execution passes from your main program, leaps up into the function block, runs the code inside, and then brilliantly jumps right back to exactly where it left off. Just remember one absolutely crucial rule. You have to define the function before you call it. Otherwise, Python just hits the brakes with a fatal name error. Section 3. Managing the data flow, input and output.
Let's talk about how data moves. Think of arguments as your raw materials. These are the actual values handed off by the caller. Parameters, on the other hand, are the precise receiving bins built into the function header to catch them. The unbreakable rule here? Those receiving bins must match the exact order of the incoming materials.
Here's a really cool behind-the-scenes secret. If we use Python's built-in ID function, we get absolute proof that the argument and the parameter point to the exact same memory location. They are staring at the exact same data sphere. It's only when you modify or reassign the parameter inside the function that it breaks away into its own isolated memory space. Now, if you want to skip providing arguments sometimes, you can set default parameters as a fallback. But watch out for the trailing rule because it's a massive pitfall for beginners. You cannot trap a non-default parameter behind a default one. It causes positional ambiguity. So defaults must strictly sit at the very end of your header. When the job is done, returning functions send a value back to the caller. And Python does something pretty beautiful here. It effortlessly packs multiple return values, like an area and a perimeter, for example, into a single cardboard tuple package. When it arrives, the caller seamlessly unpacks it into separate variables. It's an incredible time saver. Section 4. Understanding variable scope. Factory zoning. To prevent utter chaos in your code, Python enforces strict zoning. Local scope is like a closed room. Variables created inside only exist while the machine runs, and then they vanish forever. They are totally invisible to the outside. Global scope, however, is the permanent factory floor. It's accessible to everyone. But what happens if they share a name? The local variable fiercely takes priority, basically hiding the global one while you're in that room. But what if you absolutely must alter a permanent global variable from inside your temporary local room? Python's safe default is to just create an isolated local copy. To override this, you use the global keyword. It acts as a breaching connection, telling Python, hey, no local copies. Route my changes directly to the permanent factory floor. Section 5. Expanding your Python toolkit, standard and custom modules. The great news is, you rarely have to start from scratch. Python comes packed with a built-in tool belt called the standard library. Right out of the box, you have immediate access to input and output mechanics, rapid data type conversions, high-level math, and sequencing tasks. It's your ever-present foundational toolkit. When you need specialized power, you call in outside supply chains.
You can use a full import, like import math, which basically airlifts the entire external factory into your script. The catch is you have to use dot notation to find things. Alternatively, a specific import, like from math import SQR, is like a precision drone strike. It orders exactly the one tool you need, saves memory, and lets you use it immediately.
The real magic happens when you chain these tools together via composition, where the output of one function drops directly into the intake of another. Even better, you can build your own external modules. Just save your custom functions in a .py file, add multi-line doc strings to explain how they work, and you can import them into any future project. It lets you scale your capabilities infinitely. Section 6. The complete modular ecosystem, bringing it all together. Let's step back and look at the entire ecosystem operating in total harmony. You use independent functions to shatter monolithic code. You maintain clear data flow with arguments and parameters. You enforce strict environment control with variable scope to prevent data corruption. And you pull from the extended ecosystem so you never have to reinvent the wheel. It is one beautifully well-oiled machine. So you now hold the blueprints to write drastically less code, eliminate redundancy, and build highly resilient systems. The only question left is, how will you re-engineer your next Python project? Thanks for joining me on this explainer. Now go build something modular.